Our bodies are constantly performing this incredible high-wire act. On one side, we have to instantly seal any breach in our blood vessels to prevent catastrophic bleeding. But on the other, we have to prevent that very same sealing process from going haywire and causing a deadly clot. This is the fascinating story of hemostasis and thrombosis, literally two sides of the same powerful biological coin.
So this brings us to the central question of our entire explainer today. How can one single biological system be responsible for both life-saving repair, which we call hemostasis, and at the same time life-threatening disease, which is thrombosis? Well, as we're about to see, it all comes down to balance and incredibly precise control.
Let's just be crystal clear on the terms. On one hand, you have hemostasis. This is the good guy, the physiological, controlled, and localized response to an injury. On the other hand, there's thrombosis. This is the same biochemical machinery, but it's gone rogue, activating pathologically inside a perfectly intact blood vessel. The difference between life-saving and life-threatening is all about regulation.
Okay, so this whole process, this equilibrium, really unfolds in three distinct acts. First, there's the formation of an initial rapid platelet plug. Then comes the reinforcement phase, where a strong fibrin mesh is built. And finally, you have the dissolution of that clot once the healing is done. Let's dive into phase 1.
First up is what we call primary hemostasis. This is the cellular phase, the immediate response. You can think of it like the emergency first responders arriving at the scene of an accident. And the key players here, the real heroes of this initial phase, are the platelets.
Now, this initial plug doesn't just form randomly. It's a highly choreographed four-step sequence. It all begins with adhesion, where platelets first grab onto the injury site. This triggers their activation by local chemical signals. That signal is then amplified inside the platelets themselves, which finally leads to aggregation, where they all bind tightly to one another, forming that initial plug.
And the way this adhesion works is just remarkable, especially under the high-speed conditions of flowing blood. A platelet's glycoprotein complex, GPIB-XV, can't just grab onto exposed collagen directly. The flow is too fast. Instead, it latches onto this amazing bridging molecule called von Willebrand factor, which is already anchored to the vessel wall. It's basically a molecular grappling hook, absolutely essential for snagging those platelets as they rush by.
So once it's anchored, the platelet gets activated by this superpotent enzyme called thrombin. This binding kicks off an internal G-protein signaling cascade, which in turn activates an enzyme called PLC-beta. Now this is where the magic happens. This enzyme creates two critical internal signals, or second messengers, known as IP3 and DAG. These molecules are the internal command that tells the platelet, okay, time to change shape, release your cargo, and get sticky so you can bind to other platelets.
But here's the thing. That initial platelet plug is really just a temporary patch. For a durable, long-lasting seal, it needs some serious reinforcement. And this brings us to secondary hemostasis, where this incredible enzymatic coagulation cascade constructs a robust fibrin mesh. Think of it as laying down molecular rebar to strengthen the structure.
So how does this cascade get started in the body?
Well, it's primarily kicked off by what we call the extrinsic pathway. The trigger is super specific. It's the exposure of a protein called tissue factor, which is normally hidden away from the blood but gets exposed the moment a vessel is injured.
And this trigger assembles the first critical enzymatic machine, the extrinsic tenase complex. You've got tissue factor acting as a cofactor, kind of like a helper molecule. It partners with the enzyme factor 7A. Together, with calcium, their one and only job is to activate the next guy in the sequence, factor X. And factor X is the gateway to the final common pathway.
Now, the extrinsic pathway is great for getting things started, but to generate a really robust clot quickly, you need massive amplification. That's where the intrinsic pathway comes in. And this all happens on the activated surface of the platelets we talked about earlier.
This amplification step happens through a second, much more powerful complex, the intrinsic tenase. It assembles right there on the platelet surface, using factor 8A as a cofactor for the enzyme factor 9A. The key takeaway here is that this complex is orders of magnitude more efficient at activating factor X. It creates this explosive burst of coagulation right where it's needed most. Okay, so both the extrinsic and intrinsic pathways converge on one goal, activating factor X. This activated factor X then forms yet another complex, the prothrombinase complex, which generates that huge burst of thrombin we mentioned. Thrombin is really the master enzyme of this whole process. It does two critical things. It snips soluble fibrinogen into fibrin monomers that automatically assemble into a mesh, And it activates factor 13A, which then stitches that mesh together with covalent bonds, making it incredibly strong and insoluble. So you can see how incredibly powerful this cascade is, which means the body absolutely must have a way to apply the brakes, right? You have to prevent this clot from just spreading uncontrollably through your entire circulatory system, and that is the crucial job of several very sophisticated physiological anticoagulant systems.
The body uses three main strategies to keep this in check. First, you have antithrombin. It acts like a direct police officer, seeking out and neutralizing key enzymes like thrombin and factor XA. Then you have the protein CNS system. It's a bit more subtle. Instead of hitting the enzymes, it inactivates the cofactors VA and VIA, basically dismantling the amplification machinery. And finally, you have TFPI, which goes right back to the source and shuts down that initial tissue factor trigger.
Now here's a fascinating bit of biochemistry. For many of these proteins to even work, both the clotting factors and some of the anticoagulants, they need a special modification that absolutely depends on vitamin K. This process adds an extra carboxyl group to create something called a Gla domain, and this domain is what allows these proteins to use calcium as a bridge to bind to the platelet surface, localizing the entire reaction right at the site of injury. It's incredibly elegant.
All right, so the vessel wall is repaired and the clot has served its purpose. It can't just stay there forever, right? It has to be cleared away. This final phase is called fibrinolysis, and we'll also quickly touch on the clinical consequences that happen when any part of this delicate hemostatic balance gets disrupted.
Fibrinolysis is basically the demolition crew. It has its own pathway. An activator, called TPA, finds an inactive precursor called plasminogen that's already trapped inside the clot. It activates it, turning it into the enzyme plasmin, and plasmin acts like a pair of molecular scissors, systematically chopping up the fibrin mesh into little soluble fragments that can be washed away. And of course, this system has its own inhibitors to make sure it doesn't start breaking down the clot before the repair job is finished.
So what happens when some of these molecular parts are missing because of a genetic defect? Well, the consequences are severe. If you're deficient in factor VIII or I9, those key amplification cofactors, you get hemophilia A or B. If you have defects in von Willebrand factor, that molecular grappling hook we talked about, you get another major bleeding disorder because that very first step of platelet adhesion is impaired.
And of course, understanding these pathways so precisely is what allows for targeted medical intervention. To prevent unwanted clots or thrombosis, we can inhibit specific steps. Aspirin, for example, blocks a key amplification signal inside the platelets. Warfarin cleverly targets the vitamin K recycling pathway, which prevents that crucial gamma carboxylation we talked about, effectively hobbling many of the key clotting factors.
The source material gives us this absolutely fantastic analogy to tie this all together. Think of the hemostatic system as a precision automated structural repair crew. The platelets are the first responders, quickly setting up a temporary patch. The coagulation cascade is the heavy machinery pouring the molecular concrete, that's the fibrin. The supervisors, like antithrombin, are the shutoff valves, making sure the concrete doesn't fill the entire vessel. And finally, the cleanup crew, plasmin, arrives to dissolve the barrier once the job is done.
So, when you boil it all down, it all comes back to this dynamic three-phase equilibrium. You've got plug formation, you've got mesh reinforcement, and you've got controlled dissolution.
And that really brings us back to our central theme, the most crucial point of all. The ultimate difference between health and disease, between a life-saving clot and a deadly one, is nothing more than the precise, exquisite regulation of these incredibly powerful biochemical events. It is all about balance. And this really leads us to the central challenge, the holy grail of anticoagulant therapy today. Knowing this intricate balance, how can we possibly design drugs that selectively inhibit pathological thrombosis, the unwanted clot, without completely disabling the physiological hemostasis we need to survive an injury? Developing these so-called smart anticoagulants, ones that can actually tell the difference, well, that is the next great frontier in this entire field.